You are halfway through your morning commute when the train violently lurches to a halt. The cabin goes dark, and a muffled voice crackles over the intercom, blaming the delay on signal problems. That vague, everyday excuse masks a staggering reality. Beneath the concrete, this multi-billion-dollar transit network is kept alive by mechanical relays built during the Great Depression, paired with routing software running on an IBM operating system from the late 1980s. You can find the physical embodiments of these aging ghosts inside subterranean control centers, like Manhattan's West 4th Street Tower. We navigate the streets above using 5G smartphones, while the multi-ton steel vehicles moving us below rely on 19th century physical principles to avoid collisions. To understand why, we have to look back to 1872. Early railway signaling had a lethal flaw. If a wire broke or a battery died, the circuit opened, and the external signal falsely displayed a green light to oncoming trains. Civil engineer William Robinson solved this with the closed-track circuit. He ran a continuous electrical current from a battery through the steel rails to a heavy magnetic relay coil that actively held the green signal open. When a train enters that section of track, its steel axle acts as a bridge. The axle shorts the circuit, the coil loses its magnetic grip, and gravity drops the signal to red. This created an absolute failsafe. If a battery dies, a wire snaps, or a relay degrades, the coil loses power and gravity forces the signal to red, stopping traffic. Robinson's mechanism prioritizes safety with such elegant physical certainty that its extreme brittleness is exactly why modern commutes are plagued by cascading delays. Any minor hardware fault automatically shuts the entire local system down. Keeping these aging failsafes operational today requires transit authorities to scavenge for obsolete parts. The physical stakes of unchecked momentum make that impossible. In 1918, the wooden train on the Brooklyn Rapid Transit line entered a tunnel curve at roughly 5 times the speed limit. The resulting derailment under Malbone Street killed nearly 100 passengers, forcing regulators to mandate automated speed enforcement. Decades later, the 1991 Union Square derailment proved that trackside signals were no longer enough. A speeding, impaired operator blew past the external warnings, too fast for the mechanical trip arms to halt the train in time. Relying on a fixed geographic block outside the train left a fatal blind spot. To enforce continuous compliance, the safety mechanism had to move inside the vehicle itself. By the 1950s, railroads began rolling out pulse code cab signaling. This technology bypassed the external stoplights and moved the track's logic directly into the locomotive engineer's cabin. Instead of illuminating a trackside light bulb, the rails transmit invisible, coded alternating current pulses to an inductive receiver beneath the train. If the engineer ignores a restrictive code, the system takes over. A warning flashes, and penalty brakes automatically lock down the train. Yet cab signaling still relies on rigid, geographically fixed sections of track. Because the system assumes a block is either entirely empty or entirely full, dispatchers have to leave massive, inefficient gaps between trains. Solving that required a digital leap to communications-based train control and positive train control. These systems abandon the fixed physical blocks and copper wires entirely, replacing them with continuous radio links and fiber optic networks. The rigid physical block dissolves into a fluid digital bubble. Onboard computers constantly calculate exact speeds and predictive braking curves, allowing trains to run inches apart at higher speeds without sacrificing safety. Untangling the Victorian web to install this digital architecture is a staggering institutional war. New York's MTA projects it will take 50 long years and $20 billion to fully modernize its network. Crews must retrofit highly delicate radio antennas and server racks inside century-old, damp tunnels filled with conductive steel dust, extreme temperature swings, and active high-voltage rails. The freight sector provides proof of concept. In 2022, Union Pacific successfully retired its legacy cab signals across key corridors, proving that massive, heavy rail networks can operate reliably on dynamic digital logic. Locally, the results are already clearly visible. New York's L and 7 subway lines now run on communications-based train control, pushing significantly more trains per hour through the same physical tunnels with fewer delays. The transition is agonizingly slow and financially draining, but the massive capacity gains make it a strict survival imperative for any growing megacity. The immediate future of urban transit will lean even further into this shift by leveraging 5G wireless networks, Wi-Fi, and precision axle counters to successfully finalize the abandonment of physical track circuits. The safety block has evolved from a man riding on horseback ahead of a steam engine, to a heavy iron relay dropping under its own weight, to a stream of invisible data navigating through the dark. The modern metropolis is bound by its invisible foundations. The sleek, futuristic megacities we inhabit today still ride on the ghosts of Victorian engineering.